last video, we looked at Caesar cipher. Caesar cipher is an encryption scheme. And quickly to recap, Caesar cipher consisted of two things. First is the encryption algorithm. The algorithm was that the characters are going to be shifted, right? So if the input string is ABC, the output string would be BCD if k is equals to 1. So that is, each character over here is shifted by one character. So A becomes B, C becomes D, and so on. And if k is equals to 2, now this becomes CD. So this was the Caesar cipher. Again, to quickly recap, it consisted of an algorithm and a secret key. If both of these are known, you can decrypt. And if it is known to an adversary, the adversary can decrypt as well. So we need to make sure that at least one of these two is always kept secret. Cool. The Caesar cipher works because the algorithm, even if it is publicly known, no problem, as long as the secret key is kept really secret. So by how many characters are you going to be shifting from the input string to the output string is defined by a secret key. As long as the secret key is actually kept secret, there's no way for you to go back from here to here. Right? So in this case, if you know that BCD is shifted by one character, you can move each character one backwards and still get ABC back. Right? Similarly, from CDE, you can construct ABC if you know that k is equals to 2. But if you do not know k is equals to 2, it's probably impossible for you to go from CDE to ABC. Right? So you wouldn't know unless you just try every single number. In Caesar cipher, we looked at the setup mechanism as being Caesar and the general meeting in private over dinner and exchanging the secret key. So this assumes that there's nobody else in the room, nobody else heard the secret key being exchanged, and let's say Caesar whispers into the general's ear saying, hey, k is equals to 2, right? And thereby all of the messages that are being sent will be encrypted using the secret key. But for us to be able to use an encryption scheme over the internet, we cannot assume that people are going to be meeting over dinner and they could whisper a secret key into each other's ears. So for example, if you and I have to communicate something over the internet, we probably never met in person, how do we still communicate securely? How do we still encrypt and decrypt data correctly? That's the problem statement that we're going to be talking about in this video, and we're going to be looking at what is called as Diffie Hellman Key Exchange. Right? Diffie Hellman Key Exchange is what we're going to be looking at as to how do we set this key up, k is equals to 2 or whatever, without having to whisper it into each other's ears, and we still have this information without anybody else having access to the same key. Okay, so let's quickly look at the setup. So let's say this is me, and I'm honest, and say this is you, and you are honest, and say there is a messenger that we are both using, but they are not so honest, right? So we want to make sure you and I are able to communicate some information between each other without the messenger learning anything about our communication. So that's what we want to do, and we're going to do it using DHKE. So how do I send messages to you? Especially over the internet, that's probably a wire, right? There's a wire that goes from my home to, let's say, your home. And in this setup, we're going to assume that the messenger owns this wire. So this messenger might, let's say, be the telecom provider in our area, and they of course have access to the physical wires. And whenever you have access to a physical wire, you can easily tap and listen to whatever data is flowing between the two parties on the wire. So wire is really a very insecure way of communication all by itself. Okay, so this is the setup in which you and I are connected by a wire that the messenger has access to. So whatever I'm sending over the wire, you can read it, but so can the messenger, and vice versa. We still need to exchange a key such that you and I have the exact same key, but the messenger, even though is listening to all the messages that is being passed over the wire, does not have access to the same key that you and I have. This is even possible. Let's look at it. So the first approach we're going to try is, I'll just send you the number k is equals to 2 over the wire. But the messenger can read this data as well. So they have access to k is equals to 2, you have access to k is equals to 2, I have access to k is equals to 2. This does not work. We don't want the messenger ever to learn about the key that we are exchanging. So this does not work. We can't just simply send the secret key over the wire. We need to do something a little bit more complex. So that's me, that's the messenger, that's you. Okay, so I'm going to try and explain DHKE using an analogy before we get technical. And for this analogy, I'm going to be using colors to explain the intuition and then we will expand that intuition into mathematical terms. Before I get started, this is an analogy that has been inspired by the YouTube channel Computer File. They have an amazing video on DHKE as well, which is probably better than this one. If you want to check it out, please do. But I'm still going to try and recreate as much as possible, especially in the context of ZKTLS that we're going to be looking at. Okay, cool. So the goal is you and I need to have access to the same key. In this example, you and I should have on our palettes the same color. And the messenger, even if it's looking at all the messages that we are exchanging in between, should not be able to recreate the same color on their palette, right? That is what we're trying to do. You and I need to have access to the same key, the same color, but the messenger should not be able to construct the same key or the same color. Okay, so the first thing we're going to do is select what is called a generator color, right? So let's say I'm going to select a generator color, which is this yellow, and I'm going to send it to the wire so you have access to this color. But since I sent the message to you over the wire, the messenger could have tapped into it and has the access to the same color as well, right? So this is the generator color. All three of us have access to this color. I'm going to denote the information that is available to each party by showing the color right under their respective labels. This entire thing is based on one important assumption. The assumption is, let's say we have one color and we mix another color to it. Notice how this green is different from this green. The assumption is, even if we know one of these two colors that have been mixed, it is impossible to say which is the other color mixed in it. So if you know only this color, it's impossible for you to figure out that the color that has been mixed in this region is this green. Okay. So basically what I'm saying is, once colors have been mixed, it's impossible to unmix them. Even if I know that one of the colors is yellow, I still cannot say what is the second color that was mixed into this region to get this color. So that's the assumption that I want you to believe. It's not like super scientific, but just that it's hard. It's hard enough for us to go ahead with this. So if I just give you this color and the color yellow, you will not be able to deduce this green, right? So that's the assumption that we're going to base the rest of this DHKE on. So let's get rid of this. Cool. So coming back, you, me, and the messenger have access to this generator color yellow. What I'm then going to do is I'm going to take the generator color and I'm going to select a random key. This is a private key, right? And then I'm going to mix these two colors and I'm going to send this mixed color to you. Okay, so at this point, the messenger can read it as well. So you, me, and the messenger have this yellowish green color with them. They have the generator color yellow with them. But notice I never sent this green over the wire. So neither do you know that one of the colors is green, nor does the messenger, right? Okay, so what you are going to do next is you are going to select your private key and just do the same thing back. So you're going to take the generator color, you're going to take your private blue color and send this across to me. Okay, so now where do we stand? This is information that the messenger can also read, right? So this yellowish blue, and this information has been sent to me, so I can read this color as well, obviously. Cool. So all of us have access to this yellowish blue and yellowish green, but only I have access to this green. Only you have access to this blue, right? Okay, so now here's where the magic happens. To establish a key, what we're going to do is I'm going to take the color that you sent me. This is exactly this. And I'm going to add my green color. So I'm going to add this color back in. And what you are going to do on your end is also going to be the same thing. You have these three colors mixed together, right? So essentially what you did was you took the colors that I sent you and added your own color. So basically this color is yellow plus blue plus green. This is yellow plus green plus blue, and both of these are exactly the same. So both of us have this greenish yellowish blue, right? But if the messenger were to try to recreate the exact same color, by, let's say, mixing the first message that we sent across and then the second message that we sent across, that was blue on yellow, and they have access to this color. Now, if you notice carefully, this color is distinct from this color, right? So this one is a little bit more yellow. So it is not the exact same color. It's not the same color key, if you may will, right? However, both you and I have access to the exact same color, right? Exactly the same. So even though the messenger was listening or observing all the colors that were being exchanged over the wire, they could not recreate the exact same color that you and I were able to construct, because this green and this blue, which were private keys, were never exchanged over the wire, right? Just to quickly recap, we had a generator color that was publicly known. There was a private key that I selected. I mixed the private key with the generator color, sent it to you. You took the generator color, you picked a private key yourself, mixed those two up and sent it to me. And then in your mixture, I added my private key, which is this green, and you took my mixture and added your private key, which is this blue, and both of us came to the exact same conclusion of the shared key, which is this color. And the messenger, who was listening to all of the generator color that was exchanged, the first mixture that was exchanged, the second mixture that was exchanged, but still could not construct the exact same color. So that's Diffie Hellman Key Exchange for you. This is the same intuition we are going to be using to convert this into something more mathematical. Let's say there's an operation such that A operated on B is impossible to deconstruct A and B. That's property number one. And A operated on B operated on C should be exactly equal to A operated on C operated on. So these are two important properties. We need to find a mathematical operation that satisfies these conditions. And if you're able to find a mathematical mechanism to express these same two properties, we can use that for using computers. So that's what we're going to be looking at in the next video. Thank you so much.